Next up, we have Wavelabs data scientist, Dr. Bernhard Kloter. He will talk about accurate high throughput current voltage classification of high efficiency silicon solar cells with rapid wave. Welcome to TaiyangNews, Bernhard.
Thank you. So let me share my screen. Okay, yeah, thanks, and hello everybody. I would like to talk about our latest developments on measuring high efficiency silicon solar cells, and we call this new technology rapid wave, and I'll show you some results on this. Now, first some words about our company. So Wavelabs was founded in 2011. It's a German company with two working places in Germany. So we have the headquarters in Leipzig, where we also have our production, and we have an R&D center in the western part of Germany, in Münster. About 90 employees worldwide, and we claim to be the world's largest producer of LED-based solar simulators. And what we say is that like about 30% of all newborn solar cells see their first light from a Wavelabs device. Now, looking at the future from a cell testing perspective, I picked two parts from the ITRPV roadmap. So the first thing is about upcoming technologies. So what will the future bring? And clearly, and this has been mentioned in this conference several times, so we are all going towards a future with N-type, TOPCon, and heterojunction. So devices with really high voltages and really high cell efficiencies. The other thing is that to bring the production costs down, the throughput is growing and getting higher and higher, and outlook is that we will reach, for the back end, around 2030, a throughput of 10,000 wafers per hour. Now, giving a first rough estimate, we see that we somehow need to have a measurement time well below 100 milliseconds to establish this. Now, to have some more details on this, so let's break this complete measurement cycle down. So let's assume we have 5,000 cells per hour. So with two testers, we would reach 10,000 cells per hour. So the overall time we have for the classification is 720 milliseconds. Now, assuming that the wafer needs to be transported to the measurement device, we have contacting, so that needs to be opened and closed. That will take, best case, 600 milliseconds. So we have 120 milliseconds for the complete measurement cycle. And typically, this is not only one flash, but there are several measurements going on. So we have a 1-sun step, we have a half-sun step, which is necessary for determining the series resistance. Then dark IV, which could also be combined with IR. That is especially important to get an idea about the reverse breakdown of the cell device. And then EL classification to see if, for example, there are finger interruptions or some dark spots on our cells. So that means for example, the 1-sun step, we have less than 50 milliseconds available. And so let's see what that means for the actual measurement. So Here is plotted on the left side a measurement with one of our Wavelabs testers. And the interesting thing about the LED flasher is that you can set the flashing time to your needs. So that is done on one tester without recontacting the cell. And we varied the flashing time from 1 second down to 20 milliseconds for a typical PERC solar cell. And as you see, over the complete measurement, the measured efficiency is really stable. So that doesn't seem to be a problem to measure a PERC cell with 20 milliseconds. And also, if you do a simulation of such a fast measurement with PC1D, the IV curve looks as expected. Now, what happens if you repeat this measurement with a up-to-date solar cell? So in this case, a heterojunction cell. And there you see that you run into huge problems. So again, we started at this time 2 seconds measurement time, and we went down with the measurement time again to 30 milliseconds. And you see a huge deviation from the steady state or quasi-steady state efficiency if you go down to faster measurement times. And if you do this simulation, also simulate with PC1D, you see this strange behavior. So you get an overestimation from this bump, which occurs for this very fast measurement times. And fast in this sense means already 250 milliseconds, which is way slower than nowadays measurement times. That is already way too fast for such a measurement. Now, this effect is not new. This has been described in the literature, and normally it is modeled as a internal cell capacitance. And there was also last year a nice review paper from, I think, Ceres Institute. And they said that even for modules, you need to consider uncertainties between 1 and 10% if you measure a heterojunction module. And definitely this is not acceptable to have a reliable classification of your cells in your production. Now, if you look into the literature and use the physical background about this internal capacitance, you can derive the steady state curve even if you measure with a fast measurement time. Now, here's again a simulation of this heterojunction cell. And we applied this formalism and could indeed remodel this slow reference or the steady state curve, even if we have a scan of 30 milliseconds. So this is now implemented in our cell testers. The technology is called Rapid Wave. And this is usable for all cells. So without parameter tuning, you can measure PERC, TOPCon, heterojunction cells. So all modern cell types. Now, this simulation curve looks nice. So what happens in real life if you really apply this again to our module? So this is the measurement done again, now with Rapid Wave switched on. And you see, like the orange marks, that indeed you are able to reproduce the steady state value even down to 20 milliseconds measurement time. And by looking at the IV curves, so this is now the measured IV curves, not the simulated one, you see that both IV curves, so the slow and the very fast sweep, lie on top of each other. And so this 20 milliseconds is already in this frame which you need to achieve this 5,000 cells per hour. Now there's one other point which popped up in the ITRPV roadmap, which is that not only full cells are used, but nowadays more and more modules with half cells are coming up. And a lot of manufacturers want to measure half cells in their production. We have a technology for these cut cell measurements. And so on the right side, you see a picture of such a setup. So you can measure 2 half cells. We also have a solution for third cells. So you can measure these cut cells with a single flash at the same time with our flasher, and also this measurement type is rapid wave ready. Now, going back to our estimation about this 5,000 cells per hour measurement, so I hopefully I convinced you that we solved this middle part, so we are now able to have an ultra-fast measurement. Now the question is, can we get even further? Can we get even faster? And what about this automation bottleneck? Now, there is a lot of work in the community to also work on this part, and I want to mention some solutions and also some problems with this. Now, let's assume we want to stick with our measurements, so 1 sun, half sun, dark IV and IR, and EL measurement. So the first idea which could come up would be, okay, don't stop the cell during measurement. So have a measurement on the fly. Have a contacting, but contact the cell during transportation, do the measurement on the fly, and then release the cell out of the contacting. Now, with this method, in principle, all measurements should be possible, but clearly automation will be quite tricky and could be also then likely more expensive than the current solution. And as I said, throughput is the mean to reduce the cost, so we don't want to increase the cost with fancy solutions. And also, when looking at the imaging, EL and IR may need a deblurring step if you run really fast below a camera. Now, one other solution which is often discussed is get rid of the contacting overall, have a PL camera, and do machine learning. And with this, you should be able to infer the cell efficiency from the machine learning step. So this has a potential to be a really fast process. You don't need the contacting. But on the other hand, PL systems are normally quite expensive. You still need a reference measurement for your machine learning step. And all steps which involve current, especially IR and EL, are not possible. So you have a hard problem to infer the reverse breakdown. And this is a quality control, which is really important for cells and modules. And it is really hard to get the current, the actual short circuit current from such a method. Now, another method which was shown was, okay, use an EL camera and machine learning. So benefit would be you can measure the reverse current. You still need a contacting, but maybe the contacting quality can be lower. So that means maybe you can speed up your measurement. Of course, you still need a reference measurement, and short circuit current is really hard, if not impossible. So that would mean you need like another measurement device to get some idea about your current. And to give you
1 minute,
Sorry?
if you can wrap it up
Yep.
in 1.
Yep.
Yeah,
Yep.
thank you.
So to give you an idea about this problem, I took actual production data which was known to be limited with a current, and I applied machine learning with electroluminescence data and dark IV data. And here you see like reproducing the efficiency classes like from the mean value is quite okay, but you have a huge spread in your prediction. And this is due to the mismatch between the predicted current and the actual measured current. So it means there's a lot of work to be done with this next model. Now to summarize, so I've shown you our latest results with rapid wave technology, which enables us to do ultra-fast measurement with the latest cell devices like heterojunction on full half and even 1/3 cells. We can measure with this faster than 30 milliseconds, so we are already in this regime of 5,000 cells per hour. But to get the measurement time even lower concerning automation, there is no clear winner right now. A lot of groups and ourselves are working on solutions, and we are really interested what the future will bring in this regard. And with this, I'd like to thank you for your attention. I'm happy for questions to answer.
Thank you, Bernhard. That was a great presentation. One short question. So when you're measuring 2 or 3 slices, you take the measurements at one go, like at a time, or take one measurement at a time?
So it will be one measurement flash, and so we measure the cells in parallel. So the overall measurement time will be slightly higher, about for a 30 millisecond flash, we talk about like going to maybe 40 milliseconds. But it is one measurement step.
All right. I request you to please stay on, and if you could please answer some questions. There are lots of them in the chat, so it would be really nice to have you there. Thank you so much again.
Thank you.